Bismillah ar-Rahman ar-Rahim. This is a demonstration video for our solution for the senior project. Our solution is composed of three main components: the journey planning application, and the backend component, and the card counting and behavior analysis. We will go through these components now in details.
To begin with, we will talk about the planning service we developed, including the mobile app which gathers spatiotemporal data from passengers and users, then sends to our backend server. In return, it displays to passengers of the bus system in Qatar the routes they would take to reach their destinations, starting from walking or to hopping on specific buses on specific times. It will also show users the crowdness of the density of the bus stations they will be visiting. Speaking of crowdness, we also developed a module that will be placed and perform crowd analysis in bus stations based on an input from a camera. This module is responsible for gathering the count of passengers in the station from a dense map generated from a deep learning model. Then we will further analyze a sequence of those dense maps to extract more information such as average wait time of passengers, net number of passengers hopped on and off the bus, and whether the bus has arrived or not. All of these data will be sent to the backend server or the API. We will demo this using a train station footage as it's the only relevant video we could find for such situation. And lastly, all the data gathered will be received by the API, also known as backend server. Here, we will cluster the received spatiotemporal data to detect where buses are. This is done using advanced algorithms simulated using Sumo, which took steps further to expand its functionality to increase our productivity. The dataset we used in this demo to simulate the crowd feed is generated using Sumo, which we extended its functionality to interact with GDFS data. We will show how the system will process this feed and predict the live bus location from it. Also, we will show the API interface that will enable the other components to fetch the bus live location from the backend server.
So this is the demo for the crowd analysis module using the NVIDIA Jetson Nano and the night vision camera that we would have used in case COVID-19 didn't come on a real life situation. This is already hooked up a network interface card to it to enable Wi-Fi compatibility. And as a normal computer or like a Raspberry Pi, we need to have an SD card, which we have burned the Jetson Nano operating system, which is just a modified version of Ubuntu. I have already migrated the code to this SD card along with the test video that we need. To begin with, I will connect the power supply to it, and of course, since this is a computer, I need to connect the keyboard to it, and the mouse, and of course an HDMI cable. So now since it started, I will fire up the terminal
and set it as a VNC server. So as the NVIDIA Jetson Nano is now connected, and I forgot to mention that we have a network interface card connected to it via Wi-Fi, and I've connected it to my local Wi-Fi network. So if we want to check if it's already there and get its IP address, we can mmap for it. We can see that the NVIDIA Jetson Nano has an IP address of 192.168.1.103. And when we open a VNC client such as VNC Viewer, we can connect to it via SSH over VNC port. So now we're going to run the crowd analysis module over the test case video. This video was edited to suit this example purposes, and we need to run sudo, then Python 3 main deploy. I used sudo because I already set up a swap memory for it, and to allow this process to use the swap memory, we need to enable other root privileges. The logs that we can see here are for the NVIDIA Jetson Nano results for the video tested on. This is a hash map that is sent regularly every 30 seconds to the API, which includes the necessary information such as the average waiting time, the current crowd count, the number of passengers who hopped on and off the bus, from the last time, and in case the bus in the station or not.
The first step is to demonstrate how the OTP server, the Open Panel server, is running, which is used from the journey planning application before we demonstrate the mobile application. Each request or each trip plan is using this URI here, the domain which is running locally, OTP routers default, and the group of entries data. First one is from place, the origin coordinates, the longitude and altitudes. Same thing for the destination. The time needed, which is here, is 9:11 p.m. The date is 29th of April 2020. Transit and walk, maximum walking distance in meters, and then we want to arrive by, and that's it. So we'll send the request and we'll wait for the response. So this is the response here. The most important thing from the response is the plan property here, which include everything needed from the itineraries, the group of itineraries. So for this trip, it returns 3 itineraries. Alright, for each itinerary, we have the duration in milliseconds, start time and end time in milliseconds, the walk time and transit time, and all the useful information. And we have the legs, for example, which is the mode of this leg, which is whether it's walking, or we have another one, which is bus. So this information will be sent to the mobile application to be used inside for trip planning, and that's it. So after we demonstrated how the Open Planner server is running from the backend, we'll go to the application. And first thing that the application will show us if that we want to share our location or not. In this case, if we said allow, then we'll allow the user to see all the real-time information. But if we said deny, we will only show him all the static data that comes only from the Open Entrepreneur. So in this case, we'll press allow so that it can set my location. Then we'll press this blue button down here to plan a trip. And by default, the origin is set to my current location. So to set a location in this application, we have 3 options: either by my current location, which is by default is set, or by dropping a pin. Okay, you can assign to go to any place. For example, Suq Waqif here. Okay, or we can type the location. For example, we want to go to Hamad International Airport. Okay, and the destination will be set to Hamad International Airport. Okay, and here in this one here, the application is using Google Places API. So while I'm typing, Google Places API is feeding me suggestions to my input. So Hamad International Airport will be set, and in the backend, the locations of Hamad International Airport will be set instead of the name. Alright, so as a demonstration, we'll go from Qatar University to Hamad International Airport. Alright, the default maximum walking distance is 1.5, but we'll make it 2 kilometers, and you want to arrive by, for example, 3 p.m., which is today. Alright, and then the origin is set to Qatar University, and destination is set to Hamid International Airport. Okay, now to plan a trip, we have to press this button, the blue button here, and then the application will communicate with the backend server that is running to receive all the itineraries. Okay, for this trip, we have received 3 itineraries. The first itinerary that will start at 12:58 and the estimated time of arrival is 2:58. It will show us a summary of number of transfers from bus to another, the total duration, the total walking distance is 3.14 kilometers, which is a lot. The average waiting time at each bus station is 0.08. To show other itineraries, this itinerary here, the duration is 216 minutes, walking distance is 316, average walking time is 0.14, and will take only 2 buses. The third itinerary, which is 223 minutes, number of transfers is 1. Okay, so as a demonstration, we'll take this first itinerary here and we'll select it. So we'll start at Qatar University here, we'll walk all the way to this bus station, okay, and show us the crowdness, test data crowdness at Qatar University bus station, and we'll go all around to this bus station here. In the blue route, we'll take bus number 102X, okay, and we'll board at University roundabout, and we'll alight at Taqaddum stop number 1. And then we'll take bus number 170 all the way to Al Ghanim main bus station on route number 172, 170. And all the way we'll go to Al Ghanim main bus station, okay, and take another bus, which is bus number 109. I will board at Al Ghanim bus station and we'll alight at the new airport. There are 2 walking steps that will start at Qatar University, and then the one at the airport. So bus number 109 will take us all the way to Qatar International Airport, Hamid International Airport, and that's it. Yeah, so and that is the demonstration of the trip planning. For example, if we want to take another itinerary, we'll just select it, and that's it. Each itinerary will show us the crowdness at each bus station using this heat map. And that's it. Thank you.
Bismillah ar-Rahman ar-Rahim. This is a demonstration video for the backend server. As you can see, the backend server is developed using Node and Express and MongoDB. We broke the main functionality of the backend server into 3 separate APIs. Each one of them will be responsible for one task, and we can combine the result from all of them at the end to obtain the solution for the problem in hand, which is identifying the bus locations from a feed of trajectories from the crowd. The APIs, let's go through them. The first API is the clustering API, which will take a feed of trajectory sets, and it will return the clusters in that set. A cluster is a group of objects moving together, so following certain criteria. The second API is the vehicle identification API. This API is responsible for identifying the bus trip ID from the history movement of that bus. And the third one is the map matching API, or the map service API. It's responsible for map matching a set of trajectory into road IDs representing this trajectory. This is mainly used to cancel the noise from the GPS feed we are receiving from the crowd. Now, as you can see here, all the APIs have their URLs, and we are communicating with them through API communication. When we run the server, As you can see, the server, we have logs in the server that demonstrate the state of the server. At the beginning, the server starts discovering clusters in the system. He discovers 5 clusters. Each cluster will represent a bus. And after a time step, it will start invoking the update method that will update the position of the stop based on the new feed coming from the crowd. Since we are using simulation, we increase the time step. Usually the updating method happens every 30 seconds, but due to we are using simulation, it will happen every 1 second. And we increase the simulation speed so that 1 minute in a simulation will be 0.1 minute in real time. Also, you can see that we are saving the output to a map. So what we are doing is we are saving the output we are discovering the output of the system. We are saving it to a map so that we can easily be able to visualize the state of the server. This is used only for testing. It will not be used for development, of course. You can see the red routes or the colored routes represent the predefined route that the bus in the simulation we used should follow, and the orange route represent the history movement of the bus. For this simulation, I grouped the result into a GIF file, and this is the total result, where every frame, the difference time between every 2 frames is 30 seconds in real time, in simulation time, which is 0.1 second in real time. As you can see, the system is able to identify the bus's location and track them successfully through their trip in the simulation from the start station to the ending station. Also, we can fetch the real-time location or the live location of the buses through our API interface. The API interface, first you can fetch the shape IDs and the trip IDs for all the buses. Every bus will have a trip ID representing this trip, and some trips will have more than one shape. Because going from the start or the start station to the ending station and coming back sometimes is not symmetric, so you'll have different routes, one for going from the start to end and the other one from end to start. As you can see, for trip 11 you have shape 110 and 121, 120 and 121. And if we can see here that a trip ID will have shape 110, if we fetch for that, we will get the real-time bus location. As the system is running currently, it will identify the real-time bus location, and it will update with time every time the system discover or updates that position. So if we can change that, we can get another route to 120. We can see that it will track the position of the bus, and it will update frequently when this being updated with time. We only, in our simulation, we used 5 routes, so we can check only for 5, not all the route in the system. And this concludes our video. Thank you very much.